Just take a look around you for a second. Seriously. Every single thing you can see, your phone, the chair you're sitting on, that cup on your desk, it's all the result of one absolutely critical decision. What is it made of? Today, we are digging into the designer's dilemma, that incredibly complex choice that literally shapes our entire physical world. On the surface, it sounds pretty simple, right? A bike needs to be light. A knife needs to be hard. Case closed. But what about stiffness? Or cost? Or how it resists rust? Suddenly, that simple question gets really, really complicated. And that, right there, is the designer's dilemma. So, how do you even begin to navigate this world of materials? Well, here's our plan. First, we'll break down the core problem. Then, we'll map out the classic tools engineers have used for decades. We're going to ask if AI can do it better, uncover the hidden rules that can veto any choice, and finally, we'll peek into the designer's toolbox of the future.
Yeah, choosing a material isn't just about picking strong from a list. It is a super high-stakes balancing act. One decision can make or break an entire product. You get it right, and you have something iconic like an iPhone. But get it wrong, and you end up with a product that literally falls apart in your hands.
I mean, just think about it. This one choice dictates everything. It controls how the product performs, what it costs to make, how it looks and feels, its impact on the planet, whether it's safe to use, and, whether you can even physically build the thing at scale. The wrong pick can lead to total failure, costs that spiral out of control, and a lot of unhappy customers. So, with thousands of materials, each with dozens of different properties, where does an engineer even start? Well, for decades, the answer has been this incredibly elegant tool called the Ashby chart.
And this is the really crucial point. Designers can't just invent a dream material out of thin air. They're stuck with what actually exists in the real world. You can't just wish for something that's as strong as steel but as light as a feather. You have to find the best possible compromise that's out there. And that's exactly why having a systematic way to search is so important.
Now, to compare materials apples to apples, engineers use concepts like specific stiffness. See, it's not just about finding the stiffest material or the lightest one. It's about finding the one that gives you the most stiffness for the least amount of weight. That stiffness part is measured by something called Young's modulus. It's basically just a number telling you how much a material hates being bent or stretched. Getting this ratio right is an absolute game changer for everything from airplanes to tennis rackets. And here's where it gets really clever. Engineers can boil down a complex goal like, I need a light and stiff beam, into a single number that they just have to maximize. This little formula is called the material index. It combines the properties that matter for that specific job. So all you have to do is find the material with the highest index, and boom, you found your best bet. This is how those charts bring it all to life. It's brilliant. Each of those bubbles you see is a whole family of materials. All the metals are in one area, all the polymers in another. You plot properties like stiffness versus density, and you've basically created a map of the entire material world. And that material index we were just talking about? It becomes a straight line on this map. You literally just slide that line across the chart, and the very first bubbles it bumps into, those are your top performers. It's this powerful visual shortcut to the perfect material. Okay, but Ashby charts are from a pre-digital, pre-internet world. Today, we've got large language models that have read, well, basically everything. So the big question is, can an AI just do this first now?
And you've got to understand, these two approaches could not be more different. The Ashby chart is a structured visual map built on hard, quantifiable data. An LLM, on the other hand, is like a conversational partner that pulls answers from this massive, messy sea of text. It's calculation versus conversation.
So to see which one was better, researchers at Autodesk set up a head-to-head competition. They gave human experts and 3 different AIs the exact same 16 design challenges. Things like pick a material for a heat-resistant spacecraft part, or a lightweight grip for a utensil. And for each scenario, they had to score 9 different materials on a scale of 0 to 10. The results were pretty shocking, actually. On average, the AI's scores were about 3 points off from the human experts. Now, on a 10-point scale, that's not just a little off. That is a huge gap. That's the difference between calling a material acceptable versus excellent. The AI wasn't just slightly wrong. It was fundamentally disagreeing with people who do this for a living. And the study dug into why and found 2 big problems. First, the AIs were way too optimistic. They rated almost every material as being a better choice than the experts thought it was. And second, their answers were just bland. The experts gave a whole range of scores, high and low, but the AIs lacked that nuance.
It's like asking for a restaurant recommendation and being told every place in town is pretty good. It's not helpful. Oh, and it got worse. Beyond the bad scores, the AIs were all over the place. They were inconsistent, they would change the requirements of the problem halfway through, and sometimes they just made things up, adding, and I'm quoting the researchers here, random information from nowhere. So, yeah, I don't think they're ready to take over the designer's job just yet. But let's say an engineer finds the perfect material on an Ashby chart, and for the sake of argument, an AI actually agrees. The process still isn't over. There is one final boss, one final hurdle that can veto the entire decision: the law. Right. In the world of electronics, for example, two of the biggest regulatory hurdles come from the European Union, REACH and RoHS. The easiest way to think about it is that RoHS is like a blacklist. It straight up bans certain hazardous materials from being in the final product. REACH, on the other hand, is more like a whitelist. You have to register and justify every single chemical you use or import. It's a huge deal. And these two regulations really work together. Many of the worst offenders, the most hazardous substances, are restricted by both of them. We're talking about things like lead, which we all know is a potent neurotoxin, and cadmium. This tag team approach creates a really powerful system that forces designers to think about safety and the environment from the very first sketch. It's a non-negotiable filter on every single material choice. Okay, so we've got the classic systematic charts. We have the flawed but super fast AI assistance, and we have the unbending rules of regulation. The modern designer doesn't pick just one of these, they have to master all of them. When you put it all together, you get this really powerful modern workflow. You start with the Ashby chart to find your best candidates based on pure physics. Then, maybe you use an LLM to quickly brainstorm some weird alternatives, or pull up some obscure datasheet you can't find. Next, you immediately run all of it through that regulatory filter. Is it legal? And finally, the step you can never, ever skip. You apply actual human experience and intuition to make the final call. This hybrid approach is definitely powerful, but it's about to be tested like never before. Because the universe of materials we have to choose from, it's not staying the same. It's exploding. No, that is not a typo. Using a completely different kind of AI, something called graph neural networks, projects like Genome have computationally discovered millions of new, stable materials that have never existed before. Our material map is about to become unimaginably huge. So here's the bottom line. We are walking into a new era, where one kind of AI is creating an overwhelming flood of new material options for us, while another kind of AI is offering us a pretty flawed tool to sort through them. The designer's dilemma isn't getting solved, it's getting exponentially bigger. And the real question for the future is, with millions of new options on the table, how on earth will we ever choose?